Okay, so let me begin by presenting Javier. He will be given his first lecture. Javier is a postdoc at University of Concordia in Montreal, and his lectures will be about symplectic geometry at null infinity. So we have 50 minutes for the talk, and then we have around 10 minutes for questions. Okay?
Okay, great,
Thank you,
great.
Javier.
Well, thank you. And I first of all, I want to thank the organizers for letting me participate in this great meetings. I just want to make sure that everybody sees my screen. So the topic for today will be to understand the construction of symplectic geometry on null hypersurfaces, in particular Scribe Plus. So just to do um, a brief review of what's coming. In lecture 1, we are reviewing symplectic geometry, geometry constructions. This can be like a very easy topic for many of you, but anyways, we are talking about this. Then we are reviewing the compactification of Minkowski space-time. The idea here is, again, this is very basic, but to discuss in the context of how we approach null infinity as the Cauchy surfaces goes with t going to infinity. And then we are going to discuss the symplectic geometry for Young-Mills and gravity at non-infinity, Scribe Plus. Okay, this is lecture 1. Lecture 2, we are going to discuss the extension of these phase spaces. So the main thing here is that there is geometrical information on Scribe Plus, which can be recovered via these extensions of phase spaces. So we are going to be extending phase spaces. Okay, and we are going to talk a little bit about Schuckelberg trick. So this is a trick that we use when studying these extensions, which is adding an extra field which contains some degrees of freedom regarding the parametrization of the phase space at non-infinity, and this field is now covers contains some dynamical information. And in lecture 3, we are going to discuss these extensions of phase spaces in a more broader sense, which is the covariant phase space formalism. And this formalism will allow us to understand the extension of phase spaces, in particular for gravity, in a more clear geometrical way. Okay, so this is the review. We are going through examples, and we are going to go really constructing the thing. So please stop me at any time if you have any questions. So we are going to discuss this. I'll also send the organizers some notes each day so that you can also, in the afternoon or later, you can see what we are going to talk about during the day. Okay, so you'll have the information there. The bibliography will also be in the notes, so you can see there everything. So please feel free to ask any question during the lecture. Okay, so let's start then with compactification of Minkowski spacetime. Okay, and this is a nice draw that one can take. So this is the Penrose diagram for Minkowski spacetime. Okay, we have the usual compactifications. So if we take the metric here, minus d square plus b r square, plus 2 sine square r, and here we put some this square, and here we divide by 1 plus this conformal factor set. Yes, Lucas is telling me that the notes will be uploaded in the talk section in the web page. Great. Yes, so you can look at them there. So here we have, like, this is the metric. This metric is conformal to usual Minkowski. Okay, so we will have like minus dt squared plus dr squared plus the omega s squared. So this is conformal by a conformal factor that you can compute by yourself. And the main thing here is that if we do this change of variables, so t is equal to u plus b, and r is equal to b minus u, then we can go from coordinates t to coordinates u and b, and they form this nice triangle shaped domain where the dotted line here indicates points that are not in our initial space. Okay, so what we do is we compactify it by saying, okay, we add this point which correspond to pi over 2 in u and b. We add then this segment here and the point that corresponds to spatial infinity. It will correspond to spatial infinity, and then another segment and another point. So the initial Minkowski space, okay, which when we previous to compactifying is an open space, after compactification it is a compact space. Okay, and this is the schematic domain. These points here will have different names. Okay, so this point in here is time infinity, and it was usually noted like an I plus. Okay, and then this segment in here is what is called scribe plus null infinity, future null infinity, which is our main concern during these lectures. This point will be spatial infinity, which is an I with a 0. Then this is past null infinity, and finally we have past time infinity, which is a minus. Okay, and when we compactify, these segments, okay, are diffeomorphic to R times S2. So if we are in Minkowski, four-dimensional Minkowski, this will be cylinders. Okay, so there is another nice draw that we can work here. Okay, let's draw. So here we have the point in here has the topology of S2 when viewed as the limit of scribe plus. So once we add this segment as itself, we can compactify it again and see that when u goes to plus infinity, we are moving along the r direction of the cylinder. And if we compactify that by just adding the point at u equal infinity, we are saying that this extra point that we have here has the topology of a sphere, okay, because it's the upper portion of the cylinder. Yeah? We are closing the cylinder at u equal plus infinity. The same happens here at spatial infinity, where we can close the cylinder when u goes to minus infinity. Okay, so that's another way to think about spatial infinity and time infinity. There is, of course, another ways to think about it when we take the hyperboloids of Minkowski space and we say that r goes to infinity or t goes to infinity, and we have another parametrization of those points. Okay, that's a whole story by itself, and it's interesting. And in our case, we are just considering these points as spheres. Then the same goes for scribe minus. The thing here is that we have to take the coordinate b as the parameterization. So it's just that. And so that's going to be about Minkowski compactification. The thing here is that these coordinates that we are considering on the cylinders, okay, we have R, which will be parameterized for, in terms of U in the case of scribe plus, and the sphere will be parameterized in the coordinates that we are considering the spheres in Minkowski. So, for example, if we are taking holomorphic, complex coordinates, we are parameterizing by just set bar. Or if we are considering spherical coordinates, any kind of spherical coordinates, we are writing XA, which A is an index with two possible possibilities. Okay, and the same goes for scribe minus. Okay, so this point in here, spatial infinity, again, I'm just stressing this. We can see at as the minus infinity limit for U or the plus infinity limit for B. Okay, and these two ways of thinking the same sphere is responsible for all these weird properties at spatial infinity that you can see, for example, in Strominger's work, that to match certain fields when going to spatial infinity, you have to do this antipodal map. And that's the thing with this point, that you are taking points which are outside the original manifold. Once you compactify it, you have to decide which limits you take. And of course, limits don't behave the way that we want. So if you go with U, then you have a certain field defined at this point. If you have with V, you have another type of field, and you can match both, but the matching is not trivial. Okay, it should satisfy certain conditions. In the case, for example, of Maxwell equations, you can do it by yourself. It's also in Schrodinger's papers. You have this antipodal mapping. Okay. Next, I want to discuss briefly how to go from a Cauchy surface in Minkowski to null infinity, and this can be done pretty easily. Let me draw it. So let us consider constant T surfaces. So this surface is, let's say, R T XA, okay, with T equal constant. Sorry. Constant. Okay. So this is a T equal constant surface. Okay. And if we go to infinity, that means that we want to have a parameterization of null, future null infinity in terms of some of our variables. So the natural thing to do here, or one of the natural things to do, is just to write T as U plus R, and saying that the limit T goes to plus infinity corresponds to going to the limit R to plus infinity fixing Q. Okay, so any time that we are taking some limit over a Cauchy surface when T goes to infinity, we are meaning that R goes to infinity and U goes to a fixed point. Okay, and that's schematically depicted here, where you can take this point. This point goes to this point as T increases. This point goes to this point as T increases even further. And finally, the sequence of points goes to some U equal U0 constant at scribe plus. Okay, so that's a procedure by which we take some quantities defined on a Cauchy surface at Minkowski on the original manifold, and we go to scribe plus. Okay. Any questions right now? Okay. Good. So this is all very basic, but the important thing here is to stress that these points, null infinity and spatial infinity, and all these points do not belong to the original surface, okay? To the original manifold. They are things that we are constructing when compactifying. So let us review briefly the covariant phase space formalism, like the usual covariant phase space. So let us assume that we have an action, okay, which is on some domain. Okay, so if we draw here Minkowski spacetime, we have some domain D, okay, D, which we are going to impose some conditions later. But first of all, we are just taking some action which depends on the Lagrangian. Okay, and the Lagrangian will have some fields with some internal indices and spacetime indices, all denoted by alpha, and also the first derivatives, and of course, second derivatives, third derivatives, whatever. And we have some integration over the metric on the manifold that we are constructing this theory. Okay, so this action can be seen as a functional of from configuration space to R. Okay, so that it takes any configuration for the fields phi alpha, and it gives you some real number, of course, which is integrating. Therefore, since it is a functional, we can think that its variations are tangent, okay? So we can act with tangent vectors from the configuration space to this functional, giving us the gradient of the function s. Okay, so when we write this delta s, right, what we mean by this is the exterior derivative of s with respect the configuration space. So configuration space, we can put a name to it like f. So the delta s is the exterior derivative of the function s. Function as a functional from f to r. So we have to evaluate this on some tangent vector to this space, and that is just, we put this name, just the usual thing that we associate with the variation. And this will be, as you all know, the two terms. It will contain two terms. The first one is the Euler-Lagrange. So let me write it like this, and then we have this extra thing. Plus, and now it comes a boundary term, okay? This boundary term, of course, is really important in what follows, because from here we are going to define all this the symplectic structure. So these are the well-known Euler-Lagrange equations. But we have to be really careful when we are talking about Euler-Lagrange equations and variations when we are compactifying spaces, because what are the conditions that we have to impose to this to obtain the Euler-Lagrange equations? Well, first of all, we have to say something about the variations and the boundary, because as you see here, we have a boundary term. This nabla here corresponds to a divergence of this object within the brackets. So this corresponds to the integral of in the d of this guy. And here we have the volume form associated to the boundary. So this thing, it's an index. So this thing has to be 0 in order for us to obtain the Euler-Lagrange equations. Okay. So within the phase space F, at each point of configuration space, we are just considering, okay, so we have F in here. We are at each point just considering the variations that vanish at DD. Okay, so if we consider these variations in the tangent bundle, we can define those points of this infinite dimensional manifold such that they correspond to critical points of this exterior derivative. Okay,
Sorry?
so yes.
Hi, I have a question.
Yes.
And well, the boundary in this case is right plus.
Well, no, at the beginning we are just considering some domain D,
Okay.
which is well inside Minkowski.
Okay.
Later we are going to push that to the boundary.
Okay.
Yes,
Okay.
yes.
Thank you.
Great. So we are not yet at Scribe Plus. We are discussing this in what follows. First, we are just reviewing this from the starting point of view. So we have to remember that this condition is a constraint actually on the configuration space, because we are considering only those vectors on the tangent bundle whose values at the boundary of D are 0. Okay, and on those vectors we ask that the function S has a critical point. Okay, and okay, once we have this, we can say, well, this boundary term goes away. We have some compact support for this guy. So therefore, if we are in a critical point, the quantity inside this bracket here should vanish, and we have the Euler-Lagrange equation. So far so good. But okay, when we are not in a compact setup, okay, things are going to get a little bit messy. Yes. Then once we have the solution space, so let us draw here the set of points, solutions to Euler-Lagrange equations. Okay, so once we have the submanifold, the infinite dimensional submanifold, where we have these solutions to the Euler-Lagrange equations, okay, we can define on the tangent bundle of this subspace, we can define the symplectic, well, the presymplectic potential. Okay, so this is like a play where first we restrict the tangent bundle of F, and once we have the solutions, now we are just talking about tangent bundles of the solution space. Okay, so those tangent functions they are not vanishing on the boundary exclusively. So they are arbitrary things that are tangent to gamma. Okay, so there we define the symplectic potential, which we are going to write it like a capital case. So this will be a quantity that depends on some surface, and it will be the integral of the Lagrangian alpha. So alpha. So this this object now, again, we can see it as a one form on gamma. Okay, so it's a one form. That means that it takes a vector and it gives you a number. This is a one form, and we can define the exterior derivative of this object, the exterior derivative, which will be the definition for the presymplectic form. Okay, so we start with the Lagrangian, we derive the presymplectic potential. From the presymplectic potential, we construct the presymplectic form just by taking the exterior derivative in this configuration, in this solution space. Okay, and this is a true form on configuration space. Okay, this is true form. Now, we want to say things that are a little bit with little bit substance. Okay, so let us consider now the case. So we have here some, or maybe I think that I can draw it almost immediately because I have it somewhere here. Okay, so let us consider the case where we have the domain D. So following the question by the student, so let's just consider a domain D, which is well inside Minkowski. Okay, so it is further away from the Scri plus or Scri minus. So it is, let us suppose that it is delimited by some a Cauchy surface at T prime and some other Cauchy surface at T, and then from this point to this point we have some null hypersurface H, which goes from here to here. Therefore, the boundary of D will be the hypersurface sigma T prime, sigma T, and this null hypersurface. So if we want to compute the symplectic potential, okay, so if we want to compute the symplectic potential on solution space, we have that delta S, so the exterior derivative of S evaluated at some tangent vector will be the symplectic potential at T prime plus the symplectic potential at P plus the symplectic potential at H. Okay, each one of these evaluated at this vector. Okay, but now we say, okay, let's throw this term away. Okay, because by the fall of the fields, we can assume, okay, so we are restricting even further the solution space. So if we assume that this is 0, then we'll have the usual equation. So we have that this guy and take exterior derivative. This guy won't contribute to the exterior derivative when we take here the delta S, another delta. So delta square S will be 0, and it also will be the symplectic form at sigma T prime plus the symplectic form at sigma T. Okay, each one with corresponding sign. Then what we have in here is the conservation of the value of the symplectic form when evaluated at some two vectors, different vectors. Okay, so here, for example, well, this sign is, let's put the correct signs here because this is minus because the orientation is inverse, and here also. So if we assume that this part of the presymplectic potential doesn't contribute, then what we have in the end is the conservation of the value of the symplectic form, which is the standard standard starting point for doing all these things. Again, this can be done if we are not considering what happens at null infinity and spatial infinity, because if this surface goes to let's say spatial infinity and we impose some non-trivial fall-off for the fields, then of course this will contribute. So taking into account this contribution, okay, will be like the main purpose of this lecture. So how we understand the contribution of this guy in terms of the fields and in terms of the fall-off and how to make sense of this. Okay, but without losing the physical meaning of the things, because having symplectic forms allows one to construct charges and allow us to construct Poisson brackets, and well, from there all the way up to deformation algebras, etc. Okay, so that's why it is important geometrically to understand these things. We are going to see more motivation as we go along, but the first motivation is, okay, we want to understand geometrically what happens when one have a compactified Minkowski space, and now we can no longer take this thing to go to zero, let's say, okay? And that's kind of the main point in what follows, which are the famous gauge directions and local symmetries. Okay, so the word gauge is used in many contexts and has many attributions, but for us, so gauge directions on a tangent bundle of solution space. So let's G, call it like this, be the set of vectors satisfying the following. So gamma on some hypersurface sigma. So let us call it like with a little tilde here. So these vectors satisfy that when evaluated the presymplectic form on them, yes, this is 0 for all delta phi beta on the tangent bundle. So this is our definition of gauge directions. So we say that is the collection of gauge directions. Okay. Yes.
One of the variation is like a gauge transformation, right? Or is a general, because you have two variations.
Yes, one of the variations is what we say that will be the gauge direction, and the other one is a general variation, an arbitrary variation.
The other arbitrary.
Yes. So
Okay.
delta phi beta is the one that is arbitrary, and when we compute this form, this two form on this delta phi beta, then that's gonna be 0. That means that the initial form that we define so happily is degenerate. So it has degenerate directions. And those degenerate directions are what we call gauge directions. Okay.
So the variation of phi tilde,
yes,
for the gauge field is like a partial alpha phi. It's like the derivative of a nu, for example.
Exactly. So those are gonna be some of the gauge directions that we have. Yes.
Okay.
Exactly. And we are now gonna give like 3 properties that are usually taken when we are considering a domain like this one. So if we consider some domain which is between two Cauchy slices and it has like a null boundary way far away. Okay, so when we consider that, one can make a definition consisting of 3 properties, which makes the whole thing like closed. Okay, so those definitions can be found in Lee and Wall paper, which you can see it in the notes later. And the thing is the following. So if we have the concept of local symmetry, which is kind of what I think that what you were asking about. So local symmetries will be certain gauge directions. Okay, local symmetries. So we say that delta tilde phi alpha is a local symmetry. Symmetry. If one, first of all, they form a vector space. That's kind of a technical assumption, but of course we all want that if we add two variations of a mu, it's gonna be another variation. So that's kind of technical. Third, that the variation, so if we compute the Lagrangian and we compute the exterior derivative of the Lagrangian, and we evaluate it at this delta alpha, this will give us some diversion term. So this is this guy is a codimension 1 object associated to this value, to this local symmetry. Okay. And third, which is locality. Locality. That means that if we have another one, so let's say we have tilde, okay, local symmetry, and two different sets, compact set, closed sets with non-overlapping points, so their intersection is empty. Then there exists another local symmetry such that delta phi beta on B1 is equal to the original one, and delta phi beta on the other set is 0. Okay. And this is locality, and this is important in all what follows, because you see, we can do this as long as we are not reaching infinity. This H surface here contains the fall-off of the fields, so let us push it to infinity. So it contains the fall-off of the fields, and as long as we can select two closed sets that do not intersect, we can take just the locality assumption like to be true. But in our case, if we are going to infinity and we are imposing some non-trivial fall-offs in here, so let's assume that here, I don't know, phi alpha goes to phi alpha infinity in this point, then the variation of phi alpha tilde alpha, if we want to act non-trivially in these points here, cannot be local. Okay? So we can no longer assume this condition. And this condition is critical for some of the properties that Lee and Wall show. Okay, but we nevertheless can manage to get the sense of what happens when we are not dealing with locality. Okay, and this, yes.
Just to understand the notation, in the case of the gauge field, C is 0, right? When you replace the
Yes.
the particular variation,
Yeah,
it's not
exactly.
a total derivative.
Yes.
Okay.
Which in this case, of course, for gauge fields, it's trivial, but for example,
For gravity.
for gravity, certain fall-off for gravity, etc., this will be like a highly non-trivial term, which will contribute to a lot of stuff. But we are going to see this later. Great. So having discussed that, let us go so quickly to the main property, which is that for local symmetries, so for local symmetries, and this you can find it in any like text about local symmetries and all this stuff, but Lee's and Wall's paper is really nice. For local symmetries, you have the following equation. So if you consider the nether church, so let me review. You can define this quantity. Okay, this quantity, which is the symplectic potential evaluated at this term. Of course, but here I'm just considering a symplectic potential that depends on the derivative and the fields, just on that. You can do it in more general. I'm just doing it so we can talk about something specifically like here. And if we subtract this guy here, the ZA, which is this object, this codimension one thing. If we subtract it, we'll have like a quantity that is this is the nether current associated to this local symmetry, and this is the charge. Okay, this is the charge. So one can show the following. So this is this is a functional from tangent bundle to the reals. So therefore, we can take the covariant derivative the exterior derivative in this configuration space, and we can compute the following equation, which will be so this evaluated at some beta will be the symplectic form on some Cauchy surface of delta phi beta delta phi alpha. So this equation means that whenever we compute the variation of the charge along an arbitrary direction, okay, so this guy is arbitrary. As long as we compute that derivative, then we can compute also the symplectic form on those two vectors, and we obtain the variation of the charge. This is the integrability property of the nether charges. Okay. Of course, if we don't have this property here, if this guy doesn't vanish, we're gonna have to deal with integrability in another way. The same goes for certain boundary terms in the action. If the action has some boundary terms, then we have to deal with non-integrable parts. And the main thing here is that we can simplify all this notation, and usually it is written in the following way. So delta Q for some gauge parameter lambda is equal to the symplectic form evaluated at delta and the delta lambda. So I'm pretty sure that most of you have seen this way. Of course, if you have read papers about this formal construction, you have also read the previous one, but this is kind of our main thing that we are going to use. So the message to take home is the following. This is everything considering domains which are bounded by hypersurfaces up and down, and also by some null hypersurface going to infinity, but the fields vanish quickly enough so that we can take it away from our equations, and therefore we can define pretty much straightforwardly the charges. Okay, but when you don't have that, this is the main beacon that we have to look for. So one can impose this condition to the object that we have defined, for example, at non-infinity, and from that we can construct extension of the phase spaces. So this is the main object that we are going to main equation. So when we don't know what to do, we say, okay, can we construct a charge? Can we construct a symplectic form such that they satisfy this equation? If the answer is yes, good, you can construct the extended phase space. If the answer is no, you have to do a little bit more work. Okay. So in the last minutes, I think that I have like 5 minutes or 10 minutes.
Yeah, you have 7 minutes more.
Okay, so in the last minutes, I want to talk about 2 examples. One is Young-Mills, and the other one is gravity. Okay, so the details of Young-Mills and gravity you can look at them in the notes. I'm just gonna go like directly to the result. So if we go to Young-Mills, let me get there. So we have example 1. So Young-Mills. And before going to the example, just mentioning that what we want to do is at the beginning, what one has to deal with is, okay, you have a Lagrangian, and you want to construct the phase space, the final phase space. So you have to go through all these things to construct the phase space. So first you have to take the symplectic potential and the symplectic true form. Okay, and with the Euler-Lagrange equations and the symplectic true form, you have to do the gauge fixing. Gauge fixing means choosing the particular gauge that you want to be in. So in Yang-Mills, we're going to see an example. Then once you have the gauge choice fixed, you want to do an R expansion so that you can approach non-infinity. That R expansion will give you a recursive set of equations to solve to solve Euler-Lagrange equations, and therefore you can identify the free data for your theory, and that free data will eventually parameterize your phase space. You have to do the same with the gauge transformations, because usually your gauge choice will have some field dependence on it. So you have to do the same for the gauge transformations. Once you have all that, you can say, okay, the parametrization of the phase space consistent with our fall-off and our gauge condition is the following, and you have your phase space. So that's the case for Yang-Mills. So if we have Yang-Mills, we can choose radial gauge. Radial gauge, remember that it's taking a R0. We can take light cone gauge, which is a U equals 0, or we can also the harmonic gauge, which is this equation. Okay, so in any of those cases, we have to impose these these gauges, solve the equations of motion recursively in R. Yes, so you can see it in the notes. And here just writing the results for the symplectic true form. So the symplectic true form in this with these fall-offs, the radiated fall-offs is the following. So let me write it. So we have that A. So the coordinates on the sphere. Here we have a R X A. So the limits when we are going to plus infinity is some fixed function. So we are saying that the function goes to some fixed limit at scribe plus. So we have here scribe plus, and the function goes to some fixed limit. Once we have this, when we solve the equations, and the final data will be given by these functions. So AU XA. This will parameterize the phase space, and the symplectic form will be, oh, sorry, this is radiated. It will be the integral in scribe plus of the trace delta U this should go here, delta A, and here we go the volume. Okay, so one has to remember that this volume is just du ds2. Okay, so the volume, the metric at null infinity is degenerate, but we can nevertheless define a volume form, because we just integrate in U, which parameterizes the cylinder, the R direction of the cylinder, and we integrate on the sphere, which is just integration of the coordinates that we want to put in the sphere. So this is the final thing, which of course we can just from if you go to Weinberg, or you do the symplectic form just from the beginning. This is the R going to infinity limit of the following thing. Is the usual. So if you have a Cauchy hypersurface, is So let me write it better. So this is the limit when R goes to infinity of this quantity. Okay. So we are doing the same as we do before. So we take the Cauchy hypersurface, we push it to null infinity, and we take certain follows for the fields such that they are finite at null infinity. And once you do that, you can define the radiated phase space, which is this guy parameterized by the values of the field at scribe plus this symplectic form. Okay. Yes. Oh, I thought that there was a question. Okay, so if I don't have any more time, we can continue with gravity tomorrow. But if you have any question, please.
Yeah, we have like 10 minutes for questions now. If anybody wants to ask questions, let's first thank Javier, please.
Thank you for your attention.
Okay, so we have a first question by Marcelo.
Thank you for the lecture. Very nice. I don't understand very well what is the locality requirement for local symmetries. Why
Yes.
is this? Yeah, you explain, but I don't get it very well.
Oh yes, this is so this locality thing was mainly due to Lee and Wall because they want to do certain construction, and the locality means that if you can have two different local symmetries such that one is equal to the other in a closed set, and one is zero in another closed set, but they do not intersect. So it's like
and this B1 and B2 are in the configuration space, or in the
this B1 and B2 are in Minkowski.
Minkowski. Okay. So points on the space time. So sets in the space
they are sets of points in Minkowski, and that means that, let's say we have B1 here and B2 here, and we have Minkowski. And the local symmetry delta tilde alpha is leaving like its support is here. And the support of there exists another one whose support does not contain B2. That's the locality property. It's that the support of one does not contain a closed set as long as the bigger one contains both sets.
I see.
That's why it's called locality, because you can localize the action in a closed set. Yeah.
Yes. Thank you very much.
No, and that's why when you intersect them, you cannot have spatial infinity, let's say, because it is a non-compact place.
Okay. Very good.
Yes, we can understand that. So that's an important point, because we can have, let's say, this is Minkowski, and we have B1 and B2, two Cauchy surfaces at constant T. So those are closed sets, and they do not intersect. But if we compactify, then that means that they are intersecting at spatial infinity. So we are no longer able to do this locality property, and we have to deal with it in another way.
More questions for Javier?
I have a question.
Go ahead.
Thanks, Javier, for your talk. I think I got lost at some point in the end. So you were saying that you have your symplectic form, and then you push it to the North boundary, right?
Yes.
So what I'm wondering is, like, then you're putting boundary condition at null infinity, right? At your null boundary. But that guarantees that you have a well-posed bidirectional problem or something like that, because usually people take, at the spatial infinity they put boundary condition, and you have that the symplectic form is vanishing at the spatial boundary, right?
Yes.
But then how that relates to the thing that happens at null infinity. That is something I think I never understood.
Yes, no, great question, because it goes to the point that when you see that this diagram, there's a non-trivial step which is solving the R expansion equations. So when you solve the R expansion equations, you have to be consistent in what your fall-off is. So for example, one of the radiative fall-offs are characterized by assuming that well, let's talk about electromagnetism to do it concrete. So if you take the Poynting vector, you want it to be non-vanishing at null infinity. That means that like some observatory living at null infinity will receive radiation. So if you want the Poynting vector to not be vanishing, that means that you can translate it to the electromagnetic strength. So if the Poynting vector non-vanishing, then you have some non-vanishing for for FUA. So it has some non-vanishing values at null infinity. Then what you do is, okay, I want to be of order 1 in R. So this will be like R0. Okay, because you want to receive radiation at null infinity. Since you have this fall-off for FUA, you can translate this to fall-offs in AU and AA, because they are related. And then you can use Maxwell equations with an R expansion of the coefficients, Maxwell, to solve recursively all the equations and say, okay, so if I take this guy to be a function of U and the spherical coordinates, I can reconstruct the solution from null infinity to inside. So that's the linking point from going from bulk to null infinity. You have to solve recursively, being at the same time aware of the fall-off that you are imposing. Okay, I don't know if that answers your question.
I think I understand, but what I don't get is like, then you're putting some boundary condition at null infinity that allows you to have radiation, but
yes,
does that guarantees that at the spatial boundary you have a vanishing symplectic form?
No, it's not the case. So one of the main things is that this guy, if you take the limit when u goes to minus infinity of AA, is not 0. So it's actually a function on the sphere.
Okay.
It's actually a function, and that implies that all the usual machinery that you have to use is partially correct, because now you have some non-contributing thing in the spatial infinity. That non-contributing thing is the main topic of Strominger's first paper, which is the infinite dimensional charges for electromagnetism, because you have something that is non-trivial acting in spatial infinity. So yes, the question is, so the answer is you have to deal with it, adding these new symmetries, because you have something non-zero.
I see. Great. Thanks.
I guess we have time for one more question, a quick one. Somebody. Okay. If not, we thank Javier again, and
Thank you for.
we'll have a short break of 10 minutes, and then we'll come back for Lucia's Cabrera's talk. Okay. Thank you again, Javier.
Thank you. Thank you all of you for your attention. Bye.
See you guys in 10 minutes.